Okay, so in this video we're going to talk about energy and rotation together and applying our conservation of energy concepts to rotation. So the first thing we're going to do is we're going to look at some more parallels. So um, with linear linear quantities, we know that work is equal to the integral of force times the displacement, and so the rotational comparison is that work is equal to the rotational quantities of torque with respect to the angular displacement. So this would be linear displacement versus angular displacement. And so here, work is also equal to, in both cases, the change in kinetic energy. And remember, we have both rotational and linear kinetic energy. With work, if it's a uniform force, then we don't have to integrate, we just multiply the force times the displacement. And the same thing here, if it's a uniform torque, we multiply the torque times the angular displacement. Okay, and the last thing we're going to look at real quick is power. So remember that power is work over time. Okay, well, same thing here, power is going to be work over time. But the thing that will be different is that we can find instantaneous power by multiplying force times velocity. So for rotation, that would be torque times angular velocity. Now this is kind of the key. When we talk about instantaneous power, this is probably the thing that is most relevant or makes the most sense to you, because this is when you hear a car commercial and they say it has X amount of horsepower, that has to do with torque and angular velocity, okay, that they're looking at there. So they're kind of talking about the car's ability with torque and so on. Okay, so these are some parallels. We won't focus too much on power. What we're really going to be focusing on is conservation of energy with rotation. Okay, so we have a system here in which we have a rod and a hoop that are attached at an axis, so they're going to rotate about this x-axis. So you can imagine if it was like this fixture that's going to kind of fall forward, it's going to kind of, let me change the color here. So if this is the x and y plane, it's going to rotate in this kind of z plane around this x-axis. It's going to kind of fall forward, and we want to find out how fast it's moving when it flips over. Okay, and so the way that we can do this is by focusing on energy. So when it falls downward, we're going to have a change in potential energy, and that change in potential energy will cause an increase in kinetic energy. Okay, and so what we'll do here is we're going to go ahead and do this calculation and figure out how fast it would be moving, what our angular velocity would be when it falls downward. Well, we know what m is, so we have a rod with mass m and a hoop of mass m, so they can have a combined mass of 2m. So we'll put in our potential energy equation 2m times g. We don't know what h is yet. And then for kinetic energy, since it's rotating, that would be rotational kinetic energy 1/2 I omega squared. So we need to figure out what I is, and then we can solve for omega. Okay, and so this will be the challenge. We have to figure out what the change in height is and what the value for I, our moment of inertia, is. Let's start with height. So height is going to really be the change in the location of the center of mass. So we have to kind of figure out where the center of mass is. So we have two objects, each of mass m. One has its center right here, the other has a center right here. So if we do center of mass calculation here, the rod has a mass m located a distance away of h, which is r plus L over 2, or this is r and this is r, so it would be 2r, and r is just equal to 0.15, so that would be times 0.3 for that one. This one has mass m and it's located at 0.0, or at a height of 0, and so we'll divide it over by a combined mass of 2m. So if we do all this, m times 0.3 plus m is going to give us, or this is going to go to 0 here, so it'd be 0.3m over 2m. Those divide out, and so we just get 0.15. 0.15 meters really as our height. Okay, as the starting height. And it's going to fall, it's going to invert itself. So it's going to go from 0.515 meters up here to 0.15 meters down there for the center of mass. So that's a total change of 0.3 meters. So we're going to say height equal to 0.3. Now we need to find I. So to find I, we need I for the disk and I for the rod. Okay, so we'll start with the disk, or it's actually a hoop. Okay, so when we do moment of inertia for a hoop like this, so we have two options for hoops. We have this option where it's rotating about a central axis here. Okay, so this one is rotating about an axis that's kind of perpendicular to the radius. Whereas in this case right here, we have an axis that is parallel to the radius. Okay, and in the case that we're looking at right now, it's going to be this one. So there is, you can tell because the rotational axis is going through the sides, so it's kind of parallel to the diameter of this. And so instead of using mr squared, we're using the 1/2 mr squared here. So then for the disk, it's 1/2 mr squared, and we'll switch back to white here. Okay, and so that would be 1/2 times mass m times r, which is just 0.15, and then squared. And so we can simplify that, and we get 0.01125 kilogram meters squared times m. Okay, and then we'll do this one here for the rod. So a uniform rod is 1/12 m times L squared. L in this case is just twice the radius, so that would be 0.3 meters. And then because this rod is off center, we're going to have to use parallel axis theorem. It's a distance of, again, the center mass is a distance of 0.3 meters away from the center from the axis of rotation. So we're going to have to do plus mh squared, where h is equal to 0.3 meters as well. So we can simplify all this now. So we simplify it, and we get that the moment of inertia for the rod equal to 0.0975. We'll add to that the moment of inertia for the disk. So we get it for the total system. That's going to be 0.01125. Okay. And we're going to end up with a combined moment of inertia of 0.09875. We'll just go to 0.09, maybe 88 kilogram times m, kilogram meter squared. Okay. So from here we can plug it in. So we know 0.0988 m. We can see the m is on both sides, so we can cancel m out. It's going to divide out, and now we can solve for omega to find out how fast it will rotate once it gets to the bottom there. All right, and we end up with 3.43 radians per second. Okay, so we have now applied conservation of energy to rotation, and it gets a little bit hairy here because we got to do the moment of inertia, and we got to think about changing centers of mass and stuff like that. It won't always be this difficult, but sometimes there's a lot of thought that has to go into doing the problem as basic as this.